A Universe Made For Me. Physics, Fine-Tuning, and Life. Geraint F. Lewis's day job involves creating synthetic universes on supercomputers. They can be overwhelmingly bizarre, unstable places. The question that compels him is, how did our universe come to be so perfectly tuned for stability and life? From Cosmos Magazine. For more than 400 years, physics treated the universe like a machine, taking it apart to see how it ticks. The surprise is it turns out to have remarkable few parts, just leptons and quarks and 4 fundamental forces to glue them together. But those few parts are exquisitely machined. If we tinker with their settings even slightly, the universe as we know it would cease to exist. Science now faces the question of why the universe appears to have been fine-tuned to allow the appearance of complex life. The question that has some potentially uncomfortable answers. The deeper we look at the universe, the simpler it appears to be. We know that everyday matter is built from about 100 different atoms. They, in turn, are composed of a dense nucleus of close-packed protons and neutrons, surrounded by a buzzing cloud of electrons. Peering deeper, we find that protons and neutrons are themselves made of quarks, of which there are 6 distinct types. But 2 dominate the universe, the up quark and the down quark. There are also 6 leptons, of which the electron is the most famous. The 4 fundamental forces glue matter together. 2 of them, the strong and the weak force, only inhabit the subatomic world. Everyday life is dominated by the electromagnetic force and gravity. These building blocks of the universe come with tight specifications, and they never vary. Wherever you are in the universe, the mass of the electron, the spread of light as an electromagnetic wave, and the strength of the gravitational force is the same. In physics, we encounter these so-called fundamental constants so often, we barely give them a second thought. We just plug them into our equations and calculate the proportions of matter and energy to our heart's content. As a cosmologist, I can use these immutable laws of physics to evolve synthetic universes on supercomputers, watching matter flow in the clutches of gravity, pulling into galaxies and forming stars. Simulations such as these allow me to test ideas about the universe, particularly to try to understand the mystery of dark energy. More on this later. This plug-and-play approach to science has also given us a masterful ability to operate in our real universe. We blasted the Rosetta spacecraft 510 million kilometers into the solar system with such pinpoint precision it could land its probe on a 3-kilometer wide speeding asteroid. We've designed an instrument so sensitive it could detect the gravitational waves reverberating from 2 black holes that collided 1.3 billion years ago. Every aspect of our modern technological world is underpinned by plug-and-play science. While our ability to make use of the fundamental constants is impressive, they also pose a mystery. Why do they have the values they do? What if? So now I invite you to join me in imagining a universe slightly different to our own. Let's just play with one number and see what happens. The mass of the down quark. Currently, it is set to be slightly heavier than the up quark. A proton is made of 2 lightish up quarks plus 1 of the heavyish down quarks. A neutron is made of 2 heavyish down quarks plus 1 lightish up quark. Hence, a neutron is a little heavier than a proton. That heaviness has consequences. The extra mass corresponds to extra energy, making the neutron unstable. Around 15 minutes after being created, usually in a nuclear reactor, neutrons break down. They decay into a proton and spit out an electron and a neutrino. Protons, on the other hand, appear to have an infinite lifespan. This explains why the early universe was rich in protons. A single proton plus an electron is what we know as hydrogen, the simplest atom. It dominates the early cosmos, and even today hydrogen represents 90% of all combined with proton of all the atoms in the universe. The smaller number of surviving neutrons combine with protons, losing their energy to become stable chemical elements. Now let's start to play. If we start to ratchet up the mass of the down quark, eventually something drastic takes place. Instead of the proton being the lightest member of the family, a particle made of 3 up quarks usurps its position. It's known as the delta plus plus. It has only been seen in the rubble of particle colliders and exists only fleetingly before decaying. But in a heavy down quark universe, it is delta plus plus that is stable while the proton decays. In this alternative cosmos, the Big Bang generates a sea of delta plus plus particles rather than a sea of protons. This might not seem like too much of an issue, except that this usurper carries an electric charge twice that of the proton, since each up quark carries a positive charge of 2/3. As a result, the delta plus plus holds on to 2 electrons, and so the simplest element behaves not like reactive hydrogen, but in helium. This situation is devastating for the possibility of complex life. As in a heavy down quark universe, the simplest atoms will not join and form molecules. Such a universe is destined to be inert and sterile over its entire history. And how much would we need to increase the down quark mass to realize such a catastrophe? More than 70 times heavier, and there would be no life. While this may not seem too finely tuned, physics suggests that the down quark could have been many trillions of times heavier. So we are actually left with the question, why does the down quark appear so light? Things get worse when we fiddle with forces. Make the strength of gravity stronger or weaker by a factor of 100 or so, and you'll get universes where stars refuse to shine, or they burn so fast they exhaust their nuclear fuel in a moment. Messing with the strong or weak forces delivers elements that fall apart in the blink of an eye, or are too robust to transmit through radioactive decay into other elements. Examining the huge number of potential universes, each with their own unique laws of physics, leads to a startling conclusion. Most of the universes that result from fiddling with the fundamental constants would lack physical properties needed to support complex life. Framework settings. As we've seen, the building blocks of the universe appear to be finely tuned. But what about the large-scale stage on which they are assembled, space and time? Our universe exists within a framework of 4 dimensions, 3 of space and 1 of time. But it didn't have to be that way. In theory, universes can be created with many other dimensions. String theory physicists believe our universe may support 7 more undetectable tiny curled up dimensions. Princeton physicist Max Tegmark argues that it is only a universe containing the 3+1 dimensions with which we are familiar that could support life. Given the diverse possibilities, we must ask again, how did our universe arrive at this sweet spot? The dark side of the universe, a primer. And there is another structural issue to consider. Our universe is flying apart. 2 things affect the rate of expansion: the amount of matter, which acts as a brake, and dark energy, which acts as an accelerator. Dark energy is winning, so our universe is expanding at an accelerated rate. What this means is that in the early days of the universe, the rate of expansion was slow enough to allow matter to condense into stars, planets, and people. But if the universe had been born with only a touch less matter, it would have rapidly expanded, thinning out to less than one hydrogen atom per universe. On the other hand, if the universe had been born with only a touch more matter, that would have caused it to recollapse before the first stars could form. In short, the early universe was on a knife edge, poised between these possible outcomes. What emerged was the Goldilocks expansion rate, not too fast, not too slow. Then there's the finely tuned level of dark energy. We know very little about this mysterious substance that fills the universe. It may be related to the weird behavior of the vacuum. Quantum mechanics predicts that the vacuum is not really empty. Particles continually pop in and out of existence, producing a background energy that seems to influence cosmic expansion. This quantum source for dark energy, often referred to as a cosmological constant, is a true puzzle. Our quantum mechanical equations predict an immense amount of energy locked up in every cubic centimeter of empty space. But what we measure is just a minuscule amount, 10 to the 120 times less than predicted. And we are lucky this is all there is, as our simulations show that if it were only a few times larger, it would have come to dominate much earlier in the universe, rapidly diluting matter before any stars, galaxies, planets, or people could form. Symmetry. Next, we come to a consideration of the symmetry displayed in our universe. In everyday life, the word symmetry describes how something stays the same when you change your viewpoint. Think of the appearance of a perfect vase as you circumnavigate the table it's sitting on. It demonstrates rotational symmetry. In physics, we find other types of symmetries hidden in mathematics. For instance, there is a symmetry that ensures the conservation of electric charge. In every experiment we perform, equal amounts of positive and negative charges are produced. Other symmetries dictate the conservation of momentum, and there are others for a whole host of quantum properties. Some symmetries are perfect, others contain slight imperfections, and we would not be here without them. In a perfectly symmetrical universe, the hot fires of the Big Bang would have produced equal amounts of matter and antimatter. This means protons and antiprotons would have completely annihilated each other as the universe cooled, leaving a universe empty of its atomic hydrogen building block. The mystery of the missing antimatter. Somewhere hidden in the physics of protons, there must be a silent asymmetry that results in protons outnumbering antiprotons by 1 in a billion. But why does our universe possess a perfect symmetry with respect to charge, but a slight asymmetry with respect to matter and antimatter? Nobody knows. If the situation was reserved for our universe was born with 0 protons but with a net excess of energy, the immense repulsive action of the electromagnetic force would prevent matter present from collapsing into anything resembling stars and galaxies. No matter which way we turn, the properties of our universe have finely tuned values that allow us to be here. Deviate ever so slightly from them and the universe would be sterile, or it may never have existed at all. What explanation can there be for this fine-tuning? Unfortunately, if you are expecting an answer, there is none, but there is much speculation. The hand of God. While this is a scientific article, we cannot ignore the fact that the universe is finely tuned for intelligent life shows the hand of the Creator who set the dials. But this answer, of course, leads to another question. Who created the Creator? Let's see what alternative science can offer. Into the Matrix. Could our finely tuned universe be a simulation? Perhaps we are just self-aware programming, tuned on some cosmic computer, How would we know? Supercomputers can simulate the workings of the universe from subatomic to cosmic scales. They let scientists predict how individual atoms bond into molecules or observe the formation of stars and galaxies, with finer details revealed as computers grow more powerful. If our own universe is also such a simulation, that could explain why it is so finely tuned. But simulations tend to be approximations of the world around them. This suggests that the universe of the simulator is even more complex than the one we inhabit. So we'd then have to ask how the world of the simulator was fine-tuned. Ultimately, this is just another version of a creator theory. Replace the fatherly white-haired being with a multidimensional personage or robot with their hands or tentacles on the keyboard of a super powerful computer. If so, we'd better hope that some multidimensional cleaner doesn't turn off this computer to plug in their multidimensional vacuum cleaner. Physics will fix it. Physics has long been an exercise in simplifying the universe. In 1865, for instance, Scottish mathematician James Clerk Maxwell brought the seemingly disparate phenomena of electricity and magnetism together under the unifying umbrella of electromagnetism. The process is still incomplete. There is an immense gulf between our understanding of gravity, which dominates the universe at large scales, and of quantum physics, which dominates the subatomic scale. Many great minds still struggle to bridge this gulf, hoping to ultimately unify all the physics within a theory of everything. The superstring theory, with its 11 dimensions mentioned above, is one of the contenders. If science can reach this ultimate goal, perhaps no fundamental constants will remain. They will all be unified within a mathematical description. If this comes to pass, and the universe could not have been any other way, the question of fine-tuning would become, why does the mathematical structure underlying the universe allow life to arise? At this point, many may throw up their hands and say, that's just the way it is, but others, such as me, will still be troubled by the question, why? Call me Legion, for I am many. What if all our what-ifs were actually played out? What if the process that brought our universe into being also created other universes, each with their own distinct laws of physics? It might seem crazy, but at the moment, our leading physical idea for the theory of everything is known as M-theory, and it suggests just that. Being at the forefront of science, the details are sketchy, but the idea is that our universe is just one of many possible universes, potentially 10 to the 500 of them, living together in what is known as the multiverse. As each of these individual universes was forged, their laws of physics crystallized from a formless haze, giving each their unique characteristics. As we have seen, we expect the vast majority of these universes to be stone-cold dead, incapable of hosting complexity and life of any form. And unsurprisingly, we find ourselves inhabiting one of the few where the laws of physics allow us to exist. But the multiverse seems so wasteful, producing so many dead, empty universes, for each one that could potentially host life. And why did it produce any life-bearing universes at all, when it would have been easy for them all to be sterile? The question of fine-tuning seems to have been pushed to a higher level. To some, the picture of the multiverse is comforting, naturally explaining the puzzle of our own fine-tuning. But at present, we have no idea whether this immense sea of universes exists, and they may always be beyond the reach of experiment and observation. If this is the case, is the multiverse more philosophical musing than robust science? The fine-tuning of our universe for life represents a true mystery of science, a mystery that appears to point to something profound lying at the heart of science. We may never find out why we are living in a just right universe, but if we ever do, the universe and our place in it will be changed forever.